This video is all about something called component form. We've talked about vector components, and now we're actually going to create those and then put our vectors into component form. So I'm going to answer the question, what is that? And then how do we do it? So component form is just another way of describing a vector. So in this form, we express the vector as the sum of its vector components. And these vector components are along very specific directions. We choose a coordinate system. And if you recall, a coordinate system is defined by some unit vectors. And so we create vector components along those unit vectors, and then we add them up. And that's the form for the component form. So if you think about what we've been doing so far, we've always been like drawing our vectors, showing their lengths, kind of defining some angles to show how they're pointing. That was something called graphical form. So like in this example here, I show a vector as an arrow, I tell you the length of that arrow, and I define some kind of angle to describe the direction of that arrow. That's all drawing stuff, graphical form. Another way of doing this is component form. It's a more mathematical approach. You adopt a coordinate system, which is a set of unit vectors, and then you express your vectors in terms of those unit vectors. This is more mathematical. There's not really drawing necessarily involved. I need to tell you what the coordinate system is, so I might draw those unit vectors. But after that, everything is mathematical. And that's the advantage of component form, is when you actually want to perform mathematical operations like adding vectors or taking dot products. It's all written down with mathematics instead of drawing. So we no longer have to like meticulously measure our arrows and make sure we're drawing them perfectly. Instead, we're going to express everything mathematically, and we'll do the math correctly. And we'll get the same answer, it's just expressed in a different way. So the focus of the rest of this, a lot more of this semester, is going to be all about component form. So these are the steps, how to express a vector in component form. First, you need to identify the vector that you want to express in component form. So you do need to know the magnitude of your vector, and you need to have some kind of information about how it is pointing. A vector is made out of a magnitude and a direction, so we need to gather that information about the vector. Then we need to choose a coordinate system. We are going to always be working in the Cartesian coordinate system. So that's x hat, y hat, and z hat. So we are going to decide how we want our x hat, y hat, and z hat unit vectors to point. So if you recall from our Cartesian coordinate system lecture, you have to obey a right-hand rule, but you're allowed to kind of rotate those unit vectors along any directions you want, as long as you maintain 90-degree angles between x hat, y hat, and z hat. And you can get the directions of those unit vectors using the right-hand rule. So after we have decided what coordinate system we want to use, we draw those unit vectors tail to tail with our vector that we are investigating. Then we need to identify the angles that our vector is making with each of these unit vectors. Then we're just going to plug all this information into a generic expression for a vector in component form. This right here is a generic expression for a vector in component form. So this is what we got to do. We gather all that information, and now we're going to use it with this expression. So you're going to see this expression over and over and over again. Start to get used to it. So here's that expression. This is what I call the first generic expression for a vector in component form. Let's use some information that we know about dot products and unit vectors to kind of simplify or create another version of this generic expression. So I know that the dot product between any two vectors is the norm of the first vector times the norm of the second vector times the cosine of the angle between them when they are drawn tail to tail. So I'm going to kind of use those definitions to transform this expression. So in this first expression, I see a vector dotted with x hat. So I'm going to replace that with the norm of a times the norm of x hat times the cosine of the angle between them. And I am going to call that angle alpha. That's the Greek letter alpha. All right, so all that stuff gets multiplied by x hat. Now I'm going to do the same thing for this next term, a vector dotted with y. So it's going to be the norm of a times the norm of y hat times the cosine of the angle between them. This angle, I'm going to give it a special name. I'm going to call this one beta. That's the Greek letter beta. And all of that gets multiplied by y hat. Likewise with that last term, I replace this dot product with the definition of the dot product. That's the norm of the first vector times the norm of the second vector times the cosine of the angle between them. This angle I'm going to call gamma. That's the Greek letter gamma. And all of that gets multiplied by z hat. All right, so I just plugged in some definitions. Let's use one more definition. We know that the norm of any unit vector is 1. So all of these terms have the norm of some unit vector. So I can replace those with the number 1, or I don't even draw anything at all. So like the norm of x hat is just the number 1. So really this expression I can simplify into norm of vector A times cosine alpha. And all of that is x multiplied by x hat. Likewise, the norm of unit vector y is the number 1. So I just get cosine A, the norm of vector A times the cosine of beta. And all of that's times y hat. And then in that last one, I get the norm of vector A times cosine gamma times z hat. So this is what I call the second generic expression for a vector in component form. And so now it might make a little more sense why we had to gather all that information. We need to know the norm of the vector we care about, like the one that we're trying to put into component form. And we need to know the angles that it makes with each of our unit vectors placed tail to tail. With all that information, we can plug that in. We'll know the norm of our vector A. We'll know alpha, beta, and gamma. And we just literally plug that information into this expression. And then what will emerge is our expression for vector A in component form. All right, so let's do that. Let's have an example here. I have vector R. It's a position vector. It's a 3-dimensional position vector. It has a norm of 12 meters. And in this chosen coordinate system, I've already chosen the Cartesian coordinate system I want to work with. Vector R is making an angle of 75 degrees with the x hat unit vector. R is making an angle of 135 degrees with the y hat unit vector. And R is making an angle of 35 degrees with the z hat unit vector. So let's use all of our steps and express this vector in component form. All right, so I already wrote down the first generic expression. Let's use our definitions of the dot product in order to get the next one. So I'm going to go through all these steps over again because I want you to see where this stuff is coming from. Definition of the dot product says the norm of the first vector times the norm of the second vector times the cosine of the angle between them, which I am calling alpha. All of that times x hat. Then in the next term, I see the norm of vector R times the norm of unit vector Y. All of that times the cosine of the angle between them, which I am calling beta. All of that times y hat. Then norm of the vector R times norm of the unit vector Z times the cosine of the angle between them, which I'm calling gamma. And all of that gets multiplied by z hat. All right, so now let's plug in what we know. We know that the norm of R is 12 meters. They tell us that the angle between R and x hat is 75 degrees. That means alpha is 75 degrees. Beta is 135 degrees. They tell us exactly in the problem statement what all these angles are. So gamma is 35 degrees. So this is all the information we needed to gather. I already drew vector R tail to tail with all of those unit vectors. You can visualize those angles that it's making. Now I'm just going to plug all this information into my expression. So vector R is going to be 12 meters times the number 1, because the norm of a unit vector is the number 1, times the cosine of 75 degrees. All of that times x hat. Now adding plus, again, the norm of vector R is 12 meters, times the norm of a unit vector is the number 1, times the cosine of 135. All of that times y hat. And now again, the norm of vector R is 12, times the norm of a unit vector is the number 1, times the cosine of gamma, which was 35, and all of that times z hat. So with one more step, I'm going to actually plug in some numbers into my calculator. 12 times the cosine of 75 degrees is 3.11. And again, the units there are meters. Don't lose your units. All of that times x hat, plus 12 times the cosine of 135 degrees is negative 8.49, again, meters, times y hat, plus 12 times the cosine of 35, I have as 9.83 meters z hat. All right, and so this final expression, that is vector r expressed in component form using the Cartesian coordinate system that I chose. That's all you got to do. So another use of expressing these vectors in component form is actually just kind of identifying the scalar components or vector components of the vectors along particular directions. So here's again our generic expression for a vector in component form. Each of these terms contains a scalar component of that vector, vector A, I think I said R before, vector A, in the particular directions that define our space. So vector A dotted with x hat, that's the scalar component of vector A in the direction of x hat, so in the x direction. A dotted with y, that's the scalar component of vector A in the y direction. A dotted with z, that's the scalar component of A in the z direction. So those are the scalar components. Remember that the vector components are just made up of the scalar component multiplied by a unit vector. So like the vector component of A in the x direction, you just take the scalar component and you multiply it by x hat. So this component form is really just showing you it literally is the sum of the vector components of a vector. And those vector components contain scalar components. The scalar component of any vector you can get by just dotting with the unit vector in the direction that you're investigating. So let's do one more example here. I have vector h, and I want to figure out the scalar component in the y direction. So in order to get the scalar component in the y direction, I need to do vector h dotted with y hat. So let's write down vector h was 6x hat plus negative 9 y hat plus 10 z hat. And I'm going to dot all of that with y hat. So now let's distribute the dot product. You've had a lot of experience doing this. I'm going to distribute the dot product. So all of those terms in the parentheses get dotted with y hat. So I get 6 x hat dot y hat plus negative 9 y hat dot y hat plus 10 z hat dot y hat. Remember that the dot product says you take the norm of the first vector times the norm of the second vector times the cosine of the angle between them. What is the angle between x hat and y hat? Well, it's 90 degrees because all of those unit vectors are perpendicular to each other. The next term I have negative 9 times the norm of the first vector. Norm of the first vector times norm of the second vector times the cosine of the angle between them. Y and y are parallel to each other because they are the same thing. So the cosine of 0 in that term right there. And now the last one, I get 10 times the norm of z hat times the norm of y hat times the cosine of the angle between them. And again, z hat and y hat are perpendicular unit vectors, so that's going to be the cosine of 90. And one last step we can do here, these terms that have cosines of 90 will go to 0 because the cosine of 90 is 0. So that first term is just a big fat 0. The next term, I have negative 9. Well, the norm of unit vector y hat is the number 1. Again, the norm of unit vector y hat is the number 1. And the cosine of 0 is also the number 1. And then this last term, 10 times the norm of z hat times the norm of y hat times the cosine of 90 is going to give us a big fat 0 because the cosine of 90 is 0. So my final answer is just negative 9. And that's how you get it. You dot it with y hat because that was the direction that you cared about. That's how you get the scalar component of any vector. And now the vector component, all you do is you take that scalar component and you multiply it by the unit vector. So the vector component of h in the y direction is just going to be that scalar component times the unit vector in that direction. So that is my answer for the second part of the question. All right, and that's all you got to do for expressing vectors in component form.